All right, one more video. Here, we want to try to look at, so we've been kind of tackling probability from like a practical approach, kind of using a lot of words, right, to try to figure out how to do all this math. So here, to kind of finish up this chapter, we want to look at the symbolic notation, kind of the formal mathematical representations of all these ideas and symbols and notation and stuff. So here we go. I'm sure lots of us are feeling like this. Probability can oftentimes be difficult. A lot of times things that are hard or seem hard are not complex mathematically. A lot of times things that seem like they should be easy are very complex, right? A lot of times probability is counterintuitive. I know it was one of the toughest classes I took in college. So if you're feeling that, right, you're not alone. So here we want to look at some formal probability formulas. Right, so like we've been using these ideas like and means multiply, or means add, not means 1 minus, and then we'll add the word given coming up in the next chapter, right? So we want to look at how can we represent these same kind of ideas that we have in green, you know, with math symbols and stuff. Something like 7 times already. So first up, right, here's what you got to know. So this symbol, right, this red upside down U thing, that's called the intersection symbol. That means and. Right, so if I were going to read this out loud, probability of A intersect B, that's the same thing as the probability of A and B. Right, and when we see this kind of big P with parentheses, that's like what is the probability of whatever's in the parentheses. You probably haven't seen the intersection much. You've seen with domain and range, right? The union symbol, because maybe you said like when you had a function that, I don't know, maybe a rational function or something. I don't know, there's an asymptote here at -1. So maybe you said the domain was like -infinity to -1 or -1 to infinity, right? So for domain, you may have seen this. And so that union symbol, that just means or. So if I said probability of A union B, that's the same thing as the probability of A or B. There we go. So let's start looking at, like, if I said and means multiply. How would we write that in formula? Try it out. Pause it up. Do it. So all we would say is probability of A and B equals probability of A times the probability of B. So this is just the formulaic representation of and means multiply. Now, one thing that's super important is this is only true if our events are independent. Or conversely, we're going to have to decide if two things are independent or not, right? We've looked at that with two-way tables, and we'll turn that into something called the independence formula. But another way to approach independence is if the probability of A and B can actually be calculated by doing probability of A times the probability of B, then that tells us events A and B are independent. So we're not going to get too deep into that right now. When we get into the independence formula and looking at maybe two variables and deciding if they're related, we'll look at how we can use this approach here, right? But that's something that's important for moving forward. Keep that in mind. Similarly, if we wanted to think about this idea or means add, right? We could write that as probability of A or B is the probability of A plus the probability of B. But this only works if our events are disjoint. And I'm going to elaborate that in a second. I don't know why I wrote this here in red, because I actually have a slide coming up for that. So, kind of recap. So probability of A and B, like this is the same thing I just wrote, but not in my sloppy handwriting. Probability of A and B is equal to probability of A times probability of B if the events are independent. There's that formula, right? And this is what I just wrote in the box. If P of A and B actually equals P of A times P of B, then we have independent events. That's literally the same thing. So here, talking about these addition rules. So the probability of A or B equals A plus B, that's only true if we have disjoint events that don't overlap. So for example, if I looked at the probability someone's favorite flavor of ice cream, I'm pointing, but you know what I mean. Someone's favorite flavor of ice cream over there is chocolate or vanilla. I take the probability of chocolate plus the probability of vanilla, right? And so that would be what, like 107 out of the total that I'm too lazy to calculate right now and clearly should have done before this video started, plus probability of vanilla would be 92 over the total. I guess it's not that much work. 107 plus 192 is 199. Plus that's going to be what, 269? So that's our total. You should like the word total. Right, and we're good. We don't have to worry about anything here because with this blue example, chocolate or vanilla, these are disjoint events, right? There's no overlap. You had to pick one of those. You weren't allowed to pick both chocolate and vanilla because, you know, you can only pick one. So here, if we have disjoint events, we can just do A plus B. We could just do chocolate or vanilla. But we've also seen examples working with two-way tables where we have events that are not disjoint. So before I even look at the formula here for this like purple situation, let's say I have events that are not disjoint. So let's say I have the probability that someone is a teen or, right, union, the probability they chose vanilla. Here, to get that numerator, right, it's going to be out of that 269. I can't just do the teen total, which is 12, 18, 63. So I can't just do the total teens, 63, plus the total vanilla, which is 92, because what happens is these are not disjoint events. There are some people who chose or who fall into both categories, right? So I can't just do teens plus vanilla because these people get counted twice, right? These 16 people got counted as teenagers and they also got counted as vanilla, right? Teen and vanilla are not disjoint. You can do both. 16 people are both teens and chose vanilla. So if we have events that are not disjoint, we always have to pay attention to that overlap. We don't want to count anyone twice. So if we don't have disjoint events, we would write our formula for addition this way. The probability of A or B, right, like teen or vanilla, is the probability of teen, probability of A, plus the probability of vanilla, B, but then we have to subtract those 16 people who overlapped. So like if I wrote this, right, probability of teen or vanilla is equal to the probability of teen plus the probability of vanilla, but then we have to subtract the overlap, the people who were teens and or vanilla. All right, so or means add, kind of basically, that's generally true, but we have to pay attention to whether our events are disjoint or not. We always have to pay attention if there's an overlap because we don't want to count anyone twice. All right. Lastly, so we've been using this idea of, right, like not means we should subtract from one. And so not is the complement, right? So A with a little c exponent here, A complement, right? That means not A. Now on a side note, like you don't need to write a bunch of math symbols on the AP exam. Like if I took the AP exam, I would not write really any mathematical notation, right? I would use a lot of words and I would use like do the problems and show the work. So you could do the whole AP exam without ever writing any of these symbols. I'm bringing this up for a couple reasons. One, if we see questions asked using these symbols on the AP exam, of course we have to know what they're asking. Then maybe, right, maybe you watch a YouTube video or take stats in college with someone else, right, where everything is explained through all this mathematical notation, right, and hopefully now you have some idea what's going on. So A complement, not A. So for example, if I said event A, let's say we're going back to our roulette wheel, and let's say event A represents the spin lands on black, A complement is not black, or in other words, the spinner lands on red or green, right? Just not black. Right? So complement just means not. And so, right, to get the probability of A complement, we subtract the probability of A from 1. For example, to make more sense out of that. If I use these examples, right, so using the same roulette context over here, the probability of A complement, the probability the spinner is not black, can be calculated by 1 minus the probability of A, or 1 minus the probability that the spinner actually is black. Right now, of course, if this were the question, like you would just think there's 20 sections that are not black out of 38. But right, I could do 1 minus the probability of black is 18 out of 38. Use common denominators and stuff. So 38 out of 38 minus 18 out of 38 right, is 20 out of 38. Now, of course, that's like overkill. That's unnecessarily complex for the probability of roulette spins not black, but that's the idea. And of course, if we do a little algebra, add a P of A on both sides, and then subtract a PA of C on both sides, we can rewrite that formula this way. So this is the mathematical equivalent of not mean subtract from 1. Have a good day.